Hello everyone, this is Ramin Rajai. The paper title is Low-Cost Sequential Logic Circuit Design Considering Single Event Double Node Offsets and Single Event Transients. In this paper, I'm going to present a background on radiation-induced soft errors in logic circuits, and then I will be presenting the proposed sequential logic circuits in this paper. And also, in final, I want to present the simulation results, the comparative analysis, and then conclude the paper. Energetic particles hitting the drain of an off-state transistor can generate a voltage pulse on the drain. In sequential logic, this may result in data corruption, the so-called single event offset or SED. In combinational logic, this pulse can be propagated through the logic in several paths and then can be latched as an erroneous data in sequential logic. This phenomenon is called single event transient or SET. In addition to SEUs and SETs, as compact layout designs bring nodes into close proximity to adjacent nodes could be affected by a single particle, which we call this single event double node offset or SED, which is the main focus of this paper. SED tolerant latches are usually divided into two categories, layout level approach and also the circuit level approach. The layout level approach usually increase the area overhead, cause routing complexities, and do not guarantee a full immunity. And circuit level approach, on the other side, usually results in area, power and delay overhead, but they can guarantee SEDU immunity. Here we can see two examples of previous SEDU tolerant latch circuits, which are SEDU immunity. SED tolerance is also achieved using two approaches with the latch circuits. SET filters at the input and SET filters or Schmitt-Trigger based SET filters at the outputs. So some of previous work uses SET filters at the input of the latch, which come with lower power consumption and but results in area overhead. But we have like the example that we are showing here. There are also some Schmitt-Trigger based approach that come with power penalties, high delay, and high area overhead. And this approach, the second one, is not that effective and is not as effective as the first one. To mitigate SED use in sequential logic, we first introduce a static storage unit capable of tolerating double node offsets. The left figure in this slide, shows the circuit diagram of a proposed toroid inverter, a 3-input 3-output inverter, which is composed of 10 transistors, as shown in the waveform. When if all the 3 inputs change, all the 3 outputs change. Otherwise, the input remain unchanged. So based on this a circuit, if we use 2 back-to-back TIs, then we can have a static storage unit, which is the base unit of the proposed latch and flip-flop circuits. So here is the proposed SEDU tolerant or immune latch designs, which is composed of 2 back-to-back TIs. And in this design, any combination of node pairs is immune against SEDUs. So here we are showing that the proposed SEDU latch is immune against all the particles striking any combination of node pairs. So we use this EU injection model that actually is a double exponential current source given here, and Uh, in this plot, we show that any combination of node pairs are robust against SEDUs. Here is the proposed SEDU tolerant and also SET filter latch circuits, the second circuit that we are proposing in this paper. In this circuit, the input D, which passes a transmission gate, is sent to X1, a delayed version is sent to X2, and a further delayed version is sent to X3. Note that SEDU tolerance of this circuit is the same as the proposed SEDU tolerant latch that we showed in the previous slides. So this circuit is able to tolerate both SDTs and SEDUs. Based on the two SEDU immune latch designs that we introduced in the previous slides, we proposed a new D flip-flop that not only is SEDU immune but is also capable of filtering out SETs. So since the circuit is based on the proposed SEDU latch design, so this flip-flop is SEDU immune, and also the master latch in this design is the SET filter circuit that we proposed in a few slides earlier. So this flip-flop is SEDU and SET tolerant. Here we compare the proposed designs with the state-of-the-art counterparts. The first table here compares the SEDU tolerant latch that we proposed with the other designs, and it offers much better DPAP, which is delay, power, and area product. And so, as can be seen here, it's much better than the previous work. The same for the proposed SEDU and SET tolerant latch design, and also the same for the flip-flop design. So in conclusion, in this paper, we proposed actually 3 sequential logic circuits, a very fast SEDU tolerant latch, and then an SEDU, SET tolerant latch, and based on these 2 designs, an SEDU tolerant flip-flop. And so with this designs, up to 61% area improvements, and up to 48% power improvements, and up to 66% performance improvements, and up to 77 DPAP improvements have been achieved with the proposed designs in this paper. Thank you for your attention.